Good afternoon, Rich Nass, Executive Vice President with Open Systems Media, leader of the Embedded Computing Design franchise. We already know that because you've seen a bunch of the videos that we've recorded with PICMG that have to do with COM-HPC. This specification, which should be launching shortly, is one of the biggest deals to hit the embedded computing industry in quite some time. It raises the performance level for COM modules, computer on modules, significantly. So in this video, we're going to talk about the specification development process. And nobody better to talk about that than Stefan Milnor, a system architect with Kontron. He's been involved with this particular spec for quite some time. He's also been involved with writing lots of specs over his time at Kontron. Hello, Stefan. How are you today?
I'm good, Rich. Thank you.
So just an overview. What does your presentation go through?
Well, it goes over standards development, both in a general way and in specific to the PICMG and to COM-HPC. And then there's also a little bit of history of how COM-Express evolved, and it makes the case for why standards committees are a good thing. Okay, hi, this is Stefan Milnor with Kontron, talking about spec development. So here's an overview of what I'm going to talk about today, a general discussion about the types of specs, COM-HPC and others, why a new standard is a good idea, some more material on how open standards are developed, then some PICMG specific development process notes, then a bit of a history lesson on COM-Express, and then some notes on how COM-HPC, how the spec evolved, and then finally a list of COM-HPC related publications. There's more than just a hardware spec. So there are various kinds of standards. Some standards are closed, meaning that you just can't get them, like Apple computer standards. They surely have standards, but they don't share them. Sometimes a standard starts out as being a closed standard and is opened up by the company, and Kontron, or a Kontron predecessor company called JumpTech, did this with the ETX standard. ETX was a computer on module standard from the late 90s based on ISA. Kontron or JumpTech wrote the whole thing. Other companies weren't involved, but at some point Kontron or JumpTech put the whole standard on its website and said anybody can make this, and a number of companies did, and it became quite a success. So that's when that happens, it's called a de facto standard. Another very notable, maybe more notable de facto standard is the IBM PCAT. IBM wrote all the technical collateral, they published it, you could buy it for not much money, and they allowed you to make it, but they held the standard. So those are closed standards. Open standards are held by a independent organization, usually a nonprofit organization like a .org. So there are quite a few of these independent standards bodies. Some are listed here at the bottom. There's the PICMG, of course. There's SGET, which is a European organization, somewhat comparable to PICMG, but not as big. There's VITA, the PCI SIG, VISA, the IEEE, USB.org, the MIPI Alliance, and there are many others. So sometimes these standards are free, like SGET. You can get any SGET standard by just going on their website and downloading it right now. The SMARC and the Q7 standard are there, and there are two others. So they're free. Some standards are available for modest fees, like PICMG charges what I would call modest fees. You can get a PDF copy of their standards for a few $100s, and you can become a member for something on the order of $2,000. And then some organizations, there's a big barrier to entry, like Visa and MIPI charge some serious money. Okay, so why a new standard? Basically, it's about I/O bandwidth and computing power. So, bandwidth is going up all the time, and computing power is going up all the time. The 5G cell phone network, brings a whole lot more data in that has to be processed somehow. Artificial intelligence needs huge computing power. There's a lot of interest in autonomous vehicles. These need lots and lots of computing power. And then there, the other embedded industry workloads for like factory floor equipment and so on. There are the billions and billions of IoT devices and sensors, and their data needs to be aggregated at the what people call the edge, and that takes a lot of computing power. So COM-HPC is great, but COM-HPC is being introduced to kind of take off where COM-HPC more or less ends. So on the right side of this slide, a little bit about technology evolution. ETX was ISA-based, COM-HPC is mostly PCI Express based. But PCI Express is moving on to Gen 4 at 16 gigatransfers per second and Gen 5 at 32 gigatransfers per second. The COM-HPC connector is kind of running out of steam. It might work with PCI Gen 4, especially with the new 16G versions from EPT and Tyco or TE Electronics. It's probably not going to work at Gen 5 at all. Also, there are other interfaces that weren't around at the time COM-HPC was defined. So there's 100 gigabit Ethernet, USB 4. And then finally, COM-HPC doesn't really offer much in the way of manageability, and that's given a lot of attention in COM-HPC. And there's actually a separate document that will be listed at the end about remote management with COM-HPC. So COM benefits, they've become the COM's computer on modules have become quite a market success. Some of the benefits are scalability. One, a single carrier design can host a low-end module or a mid-range module or a high-end module. It allows a second source strategy. So there are about a dozen vendors making COM-HPC. And if you don't like your current vendor, you can shift to a new one. You can extend the lifetime of the product by switching to a newer generation module, like maybe from a Bay Trail to a Elkhart Lake or something a few years down the road. The interfaces are well defined, very standardized. And then also pretty important is this module plus carrier approach lets companies focus on what they do well, like a medical company making sonogram equipment, can focus on the physics of that, but they're not CPU design experts, so they don't have to worry about that. They can focus on what they do well, and they can make their carrier really an odd shape if they want. Some of these medical devices have sort of semicircular enclosures and stuff, and you can do that really well with a module-based approach. There are other technologies, backplane technologies like VPX or compact PCI serial that are technically great, but they just don't fit in many situations. So on the right side of this slide, there's a little chart about the COM market. And so it's quite successful. In 2018, it's said to have been a $1 billion market. And on the right, they're projecting, this market research organization is projecting it's a $2 billion industry in 2023. So COM-HPC. Kontron's been in the modules business for at least 20 years, starting with ETX and then moving on to COM-HPC and now to COM-HPC. COM-HPC is meant to augment COM-HPC, not replace it. It kind of starts where COM-HPC leaves off. There are two pinout types on COM-HPC. There's a client pinout type, which includes 4 graphics interfaces and a healthy dose of PCI Express. It's comparable to COM-HPC Type 6, but the bandwidth, the I/O bandwidth is significantly higher, and the PCI Express lane count is about double. And so it's just generally very feature rich. The other COM-HPC pinout type is the server, and it is comparable to COM-Express Type 7, in which the graphics interfaces are discarded and the pins are used instead for numerous high bandwidth Ethernet links and additional PCI Express lane counts. So on the COM-HPC server, there can be up to 65 PCI Express lanes, which is about double of what is available on COM-Express. Okay, the development of open standards. Open standards are typically developed over time by a committee formed from numerous interested parties and companies. There's a tired old joke that a camel is a racehorse designed by a committee. It's really a false joke. The development of a standard through a committee involving representation from multiple companies works very well. And some of the benefits of multi-company based standards development are, as opposed to going it alone, you can get expertise from other companies. They might specialize in Ethernet or something that maybe is weak in your company. You can split the work. Resource issues are relieved. You don't have to put 10 people on it from your company. You can get a group of 10 from 10 different companies. Diverse views can be considered and the best ideas incorporated. And then finally, you get a more robust review of the final documents if you have lots of different people looking at them. So this slide is about the PICMG specification development process. So the actual rules are defined in a PICMG document called Policies and Procedures for Specification Development. And this slide sort of summarizes those rules, but it's a short form anecdotal summary. So the process has been divided up into 4 parts here. The 4 parts are not official PICMG terminology. It's just the way we decided to present the material. So phase 1, this is before the PICMG is involved. A company or group of companies kick around an idea for a new specification. They line up at least 3 PICMG executive member companies for the next step. So after they've kicked out that idea around and they think they have something, they go on to phase 2. And that group of 3 companies approach the PICMG technical officer and request the formation of a new technical subcommittee. And usually the technical officer says yes. He might go back and forth a bit, but he blesses the committee. Then we move on to phase 3. A call for participation is issued to all active PICMG and associate level member companies. And they respond. Usually a dozen or so respond. On COM-HPC, I think we had up to 20 companies responding. Then finally in phase 4, one of the executive level companies arranges for an organizational meeting inviting all PICMG executive and associate members. So that meeting is scheduled and held. The meetings are held on GoToMeeting or a similar platform. There isn't usually video sharing, but there's screen sharing and everybody can hear everybody else. They're usually weekly. Well, I'm getting ahead of myself. At the organizational meeting, officers are decided upon. There's a chairman, an editor, and a secretary for each subcommittee. Everyone attending has to sign a couple of PICMG agreements or formalities. There's an IPR or intellectual property rights policy, and there's a RAND or reasonable and non-discriminatory licensing policy. And these are important, and we'll see an example in a later slide. At the organizational meeting, a working name for the new spec is decided upon. The name can change later, but you have to call it something. We'll see an example of that in a moment. A statement of work is created, and then finally a meeting schedule is established. And the meetings are usually weekly. Unfortunately, they're sometimes at very awkward times because they're, in the case of COM-HPC, there are participants from Europe, North America, and Asia, so there is no good time. So continuing the PICMG spec development process, many meetings are held and the spec is worked out. COM-Express took about a year's worth of meetings. COM-HPC, it's going on 2 years. Sometimes a specialty subcommittee is needed, or more than one. In COM-HPC, we had a signal integrity subgroup, and we also had a platform management, or IPMI subgroup. And each of those subgroups they choose their chairman, secretary, and editor. The editor documents things as the spec develops, and he forms a specification document. The progress of the spec docs are reviewed every once in a while by the technical subcommittee, and hopefully they converge to a final document. When they're ready, that spec document is submitted to the larger PICMG body for general member review. Adjustments are made if they're needed, and finally the spec is released. So COM-HPC is in that general member review process right now. So hopefully we get some feedback soon and can release or adjust and release soon. So these are some historical notes on COM-Express. COM-Express work started with a Kontron initiative called ETX Express, which was to be a successor to ETX, replacing the ISA bus with PCI Express. So Kontron wanted the backing of a major vendor like Intel for the new standard. Intel at the time said, okay, we'll back you, but we want Kontron to take this spec work to an independent standards body like the PICMG. So Kontron did that in 2004. And Kontron got together with some other companies in the PICMG, and the PICMG executive members that backed the new COM-Express initiative were Intel, Kontron, PFU Systems, and Radisys. So continuing with COM-Express, here are some examples of how COM-Express became a better standard due to the participation of multiple companies. So first off, Kontron wanted to keep the name ETX Express. So the PICMG committee decided that ETX Express was too Kontron specific, and they decided on COM-Express instead. And in hindsight, even though I'm with Kontron, I think COM-Express is a better name, and it kind of conveys that this is an industry-wide spec, not a Kontron proprietary spec. Kontron had decided on the dual 220-pin Tyco free height connectors and had an initial pinout. So the PICMG group accepted the connector choice, but PFU Systems suggested a pinout change. This fellow at PFU suggested that all essential PC features be placed on the first 220-pin connector, and that the extra features be placed on the second 220-pin connector. And this was a great suggestion, and Kontron actually benefited from a lot because it allowed the development of single connector type 1 and type 10 modules. These weren't part of the original PICMG spec, but they came along and maybe in Rev 2. And that was only possible because of that suggestion by the PFU engineer. For COM-Express, both Intel and AMD participated. Both companies provided valuable technical guidance on chipset trends. Sometimes they had to dance around each other. And then Radisys and PFU made many technical contributions and had good market insight. So as a result of all those things above, COM-Express became a huge success. It's used in many industries, and it's produced by perhaps a dozen companies. So then with reference to the IPR and RAND policies, at the beginning, COM-Express was the connector was produced by only one vendor. Over time, the module standard became popular enough that other connector vendors, EPT and Foxconn, became interested. And following the RAND policy, they worked out some kind of deal with Tyco, and so they both EPT and Foxconn started manufacturing COM-Express connectors in high volume. So right now, Tyco, or now called TE Connectivity, and EPT are the mainstream COM-Express connector vendors. So moving on to some notes about the COM-HPC spec development process or experience. The early pre-PICMG work on COM-HPC was conducted through informal meetings between AD-Link, Samtec, Congatec, and Kontron in 2018, kind of in the summer. That early working group essentially selected a new 400-pin Samtec connector that they call the Accelerate family. The working group decided on 2 of these, so that yields, of course, 800 pins. So 800 pins as opposed to COM-Express's 440. The connector pin count almost doubled, and the Samtec connector is a late model device that can handle PCI Express 5, Gen 5. So the executive sponsors for this COM-HPC initiative were AD-Link, or still are AD-Link, Congatec, and Kontron. The participating members are below in the fine print: AD-Link, Advantech, Congatec, Elma Electronic, ICC Intelligent Platforms, EPT, Fastwell, GE Automation, High-Tech, Intel, Kontron, MSC, and that should read Avnet Integrated. Sorry about that. NAT, NVent, Samtec, Seiko, Supermicro, TE Connectivity, Trends Electronic, and a group from the University of Bielefeld. It's a German university, doing a lot of work with FPGAs. And then finally, VersaLogic Corporation. So some additional COM-HPC spec development notes. The name of the standard initially by that pre-PICMG working group was COM-HD for high definition. The PICMG committee, in one of their early acts, wisely changed this name to COM-HPC because it's much clearer what's going on. HD sounds like televisions. HPC is well known as an acronym for high performance computing. The 2 pinout types had different names at the beginning. The committee changed them to client and server, which are also much clearer. The PICMG officer positions for the main effort were filled as follows. The chairman is Christian Eder of Congatec. The editor is myself, Stefan Milnor of Kontron, and the secretary is Dylan Lang of Samtec. There was a signal integrity subgroup. The chairman of that group was Jim Nadolny and later Burl Best, both of Samtec. The editor is myself again, and the secretary is Burl Best of Samtec. That group did a lot of work, donated a lot of free engineering time to the PICMG doing signal integrity simulations. The IPMI subgroup, or also referred to sometimes as the remote management subgroup, the roles were filled by Jens Hagermeyer as chairman. He's with the University of Bielefeld. The editor is Martin Kaiser, also of the University of Bielefeld. There's also someone from Congatec doing a lot of work on the remote management editing work. Then the secretary is Klaus Mittermeier of Avnet Integrated. Intel attends every meeting with about 3 people, and they give us lots of valuable advice on x86 chipset trends, and especially on new topics for us, like USB 4 or the Thunderbolt version of USB. For some reason, AMD declined to attend this time around, but that's life. And the bottom note there is about signal integrity. As mentioned, lots of labor was donated. So Avnet integrated simulated Ethernet KR and NBASE-T interfaces. Avnet also provided lots of general SI advice, including developing stack-ups and various plots of interest. Intel personnel simulated the DDI digital display interfaces and the SATA interface, and they also simulated and came up with the topology recommendations for the SPI and eSPI interfaces. These, most of the interfaces are point-to-point high-speed serial links, but SPI and eSPI are different. They want something called a balance tree topology, which took a little bit of doing to work out for a module because it's hard to get the branches the same on the module and the carrier. Samtec did a lot of simulation work on PCI Express and USB, and they also provided guidance on how to break signals out of this dense BGA connector that they have. Continuing as COM-HPC, the remote management topics were covered by the University of Bielefeld and NVent primarily. Initial layout studies for COM-HPC were conducted by Avnet Integrated, Cogitech, Intel, and Kontron. Each company did their sort of what-if simulation placement study, and then compared notes. And sorry, this bottom bullet has already been mentioned a couple times. Lots of signal integrity work. And getting towards the end here, the PICMG COM-HPC committee is working on 4 documents, not just 1 document. The largest document is the one I've been working on a lot, the COM-HPC module base specification. It's basically a hardware specification. There's a parameter EEPROM that was used in COM-Express, and it's being adapted or enhanced for COM-HPC use. And so there's a document describing that, the data structures, and that's called the PICMG EEP for COM-HPC embedded EEPROM. EEP stands for Embedded Electrically Erasable PROM. Then there's a carrier design guide in the works. And then finally, there's the platform management interface specification document that's been mentioned a couple of times. So we hope to release initial versions of all 4 of these documents soon, like maybe before the end of the year or just at the turn of the year. And that's what I have today. Thank you to all the companies that sponsored this PICMG tutorial series. Those sponsors' logos are shown there. All right. Thank you. Bye.
Thank you, Stefan. That was very interesting. It was. It's always good to see the process from the beginning to the end. Those of you who are watching this video, I encourage you to watch all the others. Each looks at a different part of the COM-HPC spec. So check them all out.